Welcome back to your physics notes. So what we're going to talk about next are drag forces. These are also known as air resistance or air friction. Now, normally in physics problems, especially entry-level physics problems, we tell you to ignore air resistance. And the reason why is because for most situations, when something's not moving very quickly or it's relatively aerodynamic and small, for the big picture type stuff, the air resistance is pretty minor and doesn't really have a big impact. Now, but in reality, it kind of can. So sometimes you do want to look at it. So if you picture this, let's say you are riding along on your bicycle. And just humor me on the bicycle part, okay? Now, normally, you provide some force, friction between the tires and your grounds, between the tires and the ground, propels you forward. So let's say you have some velocity in that direction, okay? Now, if you're riding your bike and you're moving along as fast as you possibly can, and you see a big old B right there, if you keep moving in that direction, eventually, if we zoom in on this situation, so you keep moving and you get to about right here, if we zoom in, we are going to see your face and the B have a collision. Probably going to not feel very good for you, but it's going to feel really bad for the B. Now, as you apply a force on the B provides an equal and opposite force on you. So if you were moving in to the right, you had a velocity that direction, there was a force on the tires propelling you in that direction, this collision with the B would provide a little force to oppose your motion, and it might actually cause a slight acceleration, or at least decrease the net force acting forward. So that would have an impact on you. Now, what we generally ignore are all of the collisions that are happening that seem so minor. So if we zoom in on this, and now we zoom in super, super far, maybe this is the tip of your nose, and maybe you have a little pimple right there. You're actually colliding with a whole bunch of things. So this B right here was saying, no. Well, think about all of the tiny little air molecules, like right here. Maybe these are some nitrogen, so that's a nitrogen molecule. Here is an oxygen molecule. Here's another nitrogen molecule. Maybe you have some CO2, that's a C, that's an O, that's an O. Maybe you even have some water, so that's an oxygen, a hydrogen. These are all little molecules, and if they collide with you, you are going to push them all out of the way as you hit them, and as you push them all out of the way, they are going to provide pushes back by Newton's third law, so that every little molecule you push, it pushes back on you. So it makes logical sense that the faster you go, just like the more bugs you would hit, the more air molecules you'll hit. And for every little molecule you push, it pushes back and it can slow you down. So you're always smacking into these air molecules and they smack you back by Newton's third law. Newton's third law says that as you smack them, they smack you back. And that can have an impact over time. So if you think about it, the faster you're going to go, you're going to hit more air molecules, so that should make a difference. The bigger the area that you are presenting to those air molecules, right? So if you're moving this way, the bigger your cross-sectional area as you move across, the more air molecules you're going to hit. And then also the medium you're traveling through. So air itself, if you're traveling through water, it's much more dense. You would hit a lot more water molecules than if you're in the air and hitting air molecules. But there's things that can affect that even within air. The temperature of the air, the humidity of the air, and stuff like that. So as we look at this, we can get a little more complicated. And if you were to Google the drag force, you do not need to know this or use this equation, but I'm going to show it to you because it makes logical sense. The force due to drag is equal to a couple things. You have this letter rho, you have velocity, and usually that's squared, but I'll talk about that in a second. You have area, you have the drag coefficient of the shape of the object over the number 2. So these are the variables that impact it, and they kind of all make sense. The more dense the air, the more molecules you're going to hit. The faster you're going, the more molecules you're going to hit. The cross-sectional area you have, the bigger that is, the more you're going to hit. And this drag coefficient has to do with the shape and how easily they slide across rather than bump into the shape you are. Okay? So Now, when we look at this, we're not going to look at all these things. Instead, what we might have is you usually have a problem where they tell you that the force due to air resistance, the drag force, is something like this. It's equal to negative BV, or maybe negative BV squared. Now, I know this is squared up here, but what we find is at low velocities, it tends to be linear and proportional to V. At higher velocities, it tends to be proportional to V squared. It's really not that big a deal. What you need to know is that if for Physics 1 especially, if they give you a question like this, they're going to specifically tell you what it is. Okay? So it's just a force. It makes perfect sense. Now, if you think about it, if we do BV squared, well, they're giving you all of this. They're just telling you what it is. This is a big old number. Because if you think about it, the density of the air is probably not going to change. Your area is not going to change. That's not going to change. That's a number. It's not going to change. These are all constants. So they are just simplifying it down to one constant that they call B. Okay? So now a problem they might give you is what if a ball is dropped and falls to the ground? They state that the force of drag is equal to negative BV. Now, remember, drag is a force, okay, and any negative sign for a force just has to do with direction, so don't let that confuse you. What this says is the force of drag is going to be the opposite direction of the velocity that the ball is moving, okay? So, they might ask you to draw free body diagrams for different situations. So my situations they might give you are just when the ball is released, after it falls for a bit but is still accelerating, and then after it hits terminal velocity. Well, the logical question hopefully you're asking is what is terminal velocity? Terminal velocity is the speed where your drag force is equal to your weight. So essentially it's when you stop accelerating. You stop speeding up at this point because the net force acting on you is 0. So if I were to now draw my free body diagrams, here's a dot representing the ball just when released. So I've just let it go. It's interacting with the earth and it's being pulled down with the force mg, but velocity equals 0. So BV is going to be equal to 0. So there's no upward force. There's no drag because it's not moving yet. Now, later on, it still has the same weight. That's not going to change. But now it has some velocity. So that drag force is going to be equal to BV. And you see that it's still accelerating. These forces are not balanced. And then at terminal velocity or after terminal velocity, I have my weight force. But now it has gotten to the speed where this vector has grown to be equal to the length of the weight force, and now the net force equals 0, so the acceleration equals 0. Okay, so that's an example of what they might want you to do. The other thing they could ask is to find the velocity when this happens, okay? So the velocity, when it hits terminal velocity, you would apply Newton's second law, and you would say the net force is mg minus bv, because they're in opposite directions. And if it's at terminal velocity, those two vectors are equal. M times a is just going to be 0 because a is 0. So now what is my velocity? I would now just do my algebra. I would get mg equals bv. I'm just moving the bv over. And then I would divide both sides by b to solve for v. And I would get the terminal velocity, v sub t, if you will, is mg over b. Okay? So that is an example of how you might approach any problem involving drag. And keep in mind that if drag is involved, it'll either be obvious or we will specifically tell you that. All right, have a good day.